tonight we're privileged to have as our main speaker Dr. Ed Cackett. Earlier tonight we had something a little more oriented toward beginners. This will be a little higher level, just to get some balance here. Dr. Cackett received his PhD from the University of St. Andrews in Scotland, which, again, they're almost off from the UK. He has also done work at the University of Michigan and the University of Cambridge. He's now an assistant professor at Wayne State University. We're privileged tonight to have him come to speak to us on recent results from BICEP2, evidence for inflation in the early universe. Dr. Cackett.
Thank you very much for having me here. Can you hear me all right in the back?
Yes.
Yeah. Okay. So I should say my sort of research area is typically neutron stars and black holes, and this is a very different topic to that. It's really what's going on in the very, very early universe. So while this is not my research area, it's an extremely hot topic at the moment. And when the first announcement was made of these results in March this year, people got extremely excited. I would say Nobel Prize was probably uttered many, many times, right? Within just 2 weeks ago, I would say, another paper has come out that I would say makes this look less certain, right, in terms of how true these results are. So it's kind of been an interesting lesson in the scientific method, how things change. But it's also exciting as to what actually may be there, right? It's still not certain this is a 100% real result, but if it's true, it's extremely exciting. So I'll try and give you a broad introduction to the early universe, Big Bang, what inflation is, and then what this telescope at the South Pole was doing to produce this, which tells you something about gravity in the very, very early universe. So you can't talk about the Big Bang without showing this figure here. This is a famous figure produced by Edwin Hubble. I'm sure many of you have probably seen this before, right? And this plots velocity of galaxies against distance on this way. Okay? So the further away an object is, the faster it's traveling away from you. Right? This was Edwin Hubble's big discovery in 1927, and what is now has the law named after him, Hubble's law, right? So the velocity of a galaxy is equal to some constant times by the distance of the way. Okay. So the further away an object is, the faster it's traveling. It turns out Hubble actually, the results from his paper are actually completely wrong today. He used seconds to measure the distances to galaxies, right? And at the time, people didn't realize two things about Cepheid variables. Firstly, that there are multiple types. Secondly, that there's actually dust in our galaxy, right? And dust in our galaxy makes things appear fainter, and so people assume things are further away. So we actually got the constant H0 wrong by about a factor of 6 or 7, I think you know right. Yeah. So this was figured out quite a bit later, but this relation still holds, that the further away things are, the faster they travel. This is really the first clear evidence for the universe being non-static, right? At the time, everyone wanted the universe to be not changing. The famous example of this is Einstein, right? When Einstein came up with his theories of general relativity, he wrote down his equations, and he realized that his equations showed that the universe could actually collapse and into what we would now call, say, a big crunch. Right? Yeah. And he didn't like this. So he just pushed his equation, he put an extra term in there, right? The extra term got known as the cosmological constant, And that was there to balance out the fact of gravity and basically stop the universe collapsing in his equations. Because he wanted the universe to be static. Right? When Hubble came up with this, and it was realized that this implies that the universe is expanding, Einstein reportedly said that the cosmological constant was his greatest blunder. Right? Actually now, for instance, in 1998, we actually have the cosmological constant back in this equation, right? Because of the discovery of dark energy and the fact that objects are actually, distant objects in the universe are traveling faster away from us than I actually think they should have been. Anyway, so the idea is that the further back in time you go, i.e. the further away from us you are, the higher the redshift an object, the faster it's traveling. And so if you say this is showing us that the universe is expanding, you can ask the obvious question, what if I turn back the clock, right? If I have a universe that's now at some size and it's expanding, if I turn back the clock, it must have been smaller at some time in the past, right? And if you keep turning back the clock, you get this idea, well, maybe the universe started in a single point in space and time. Okay? The idea of the Big Bang. And I would say this was unfashionable, certainly until Hubble came up with this. Even after Hubble went to the 1950s and 60s, Fred Hoyle, who was probably the most famous astronomer at the time, was vehemently opposed to there being an expanding universe. He was very, very steadfast in his belief of the steady-state universe. Now it's very much agreed that the Big Bang is a sort of standard picture for what was happening, what happened, how the universe started. So, how have we come to build up this picture, and why do we believe it so strongly in it now? Well, one of the first sort of really nice demonstrations of the power of this big picture of the Big Bang was actually in predicting the amount of hydrogen and helium we see in the universe. So again, if you say the universe today was smaller in the past, and so everything was closer together, it leads you to the conclusion that the universe was much hotter in the past, right? So as you go further and further back, earlier and earlier in the universe, the idea is that the universe gets hotter and hotter and hotter, right? Now, it took Alpha and Gamow came up with the idea that the universe could have been hot enough in the past that hydrogen could fuse into helium. Okay? The same process that happens in the center of our sun. And they said, if this is the case, if the universe was this temperature, then we should expect the cosmic abundances to be the way we see them, right? And so this is showing a figure from their paper in 1948. This is atomic weight, so 0 of one big hydrogen, all the way up. And this straight line here is their model to the actual observed abundances in the universe. And their picture fits beautifully. Right? The competing model for this was actually by Fred Hoyle, who had figured out how fusion actually happens in stars. Right? But he completely underpredicted the amount of helium in the universe. Right? So his model couldn't even come close to matching this. This result basically got ignored. And I'll talk about when it was rediscovered in a little bit. Interestingly, Gamow, who was sort of led this work, worked with Hans Bethe, and he liked the idea that alpha, beta, gamma is close to the three letters of the first letters of the Greek alphabet, alpha, beta, gamma, right? And so, without Hans Bethe's knowledge, he put him as the second author on the paper. just so that it looked nice. And this paper is often referred to as alpha, beta, gamma. Okay, so this was one of the very early successes in the Big Bang theory, that if the universe was smaller and hotter in the past, it would be the right temperature to be able to produce the amount of hydrogen and helium that we currently see in the universe. Okay, so they sort of kept on working on these lines. Alpha and another collaborator, Herman, and then later Peoples and Dickey said, well, if the universe really was this hot enough to have fusion happening in the very early universe, then it should be very hot and very dense. And if it's very hot and very dense, what should happen is that the photons, the particles of light, should be able to travel very far without scattering. Right? This is what we call essentially in thermodynamic equilibrium. What we say is that in physics terms, the mean free path of the photons are very short. Essentially, the photons can't go very far without scattering off something, because everything's so hot and so dense. And then what happens is, as the universe expands, the universe gets less dense and it starts to cool down. And if you go to today, you would expect that the universe should cool down from having been temperatures hot enough for fusion, so temperatures greater than or similar to the temperature in the core of our sun, to being today they predicted around about 5 to 10 degrees Kelvin, so 5 to 10 degrees above absolute zero. So they had this idea that if this is the true picture of what happens in the early universe, there should be this radiation throughout all of the universe that's around about 5 to 10 degrees Kelvin. Okay, so, was this ever detected? Yes. This is the now famous cosmic microwave background that I'm sure many of you have heard of. But I would say the detection was kind of serendipitous, like many things have been in astronomy over the years. Right? These two guys, Penzias and Wilson, were working at Bell Labs, and their job was actually to work on a microwave antenna, a horn reflector, this thing you can see in the background. Its entire job was to communicate with the Telstar satellite, this thing here, in the early 60s. And they had this problem. Everywhere they pointed their detector in the sky, there was this constant hiss, right? And they got quite annoyed by this, and they really wanted to try and improve their detector. They thought there was a problem with the detector. So they climbed in there and realized that there were some pigeons in there, and the pigeons were doing what pigeons do, essentially leaving lots of bird poop everywhere. So they get in there and they scribble a bird poop out. Make it nice and clean, then they discover that the pigeons are homing pigeons. And they just come back and make it dirty again. And they went in and they actually take down all the sort of any disconnections between the sort of joints in the sheets of metal in there, and still they couldn't get rid of this signal. And then they learned that the calculations of Peebles and Dickey that a year before had done what Alpha and Herman had done in 1948, which was calculate that there should be this radiation that's 5 to 10 degrees Kelvin approximately that permeates all the way through the universe. And so they realized that the hiss that they'd been trying to get rid of for many, many months was actually an astrophysical signal. It was the radiation that's left from the cosmic microwave background. And so this cosmic microwave background was discovered, and they got the 1978 Nobel Prize for having made this discovery. So a few facts about the cosmic microwave background. If you look anywhere in the sky, it's almost completely homogeneous and isotropic. So it's everywhere, and it's basically the same temperature wherever you look. Once you remove the motion of the sun, so the sun is actually moving around our galaxy. Once you correct for this, the temperature is constant to 1 part and to 5, right? So this is 10 parts in a million, right? This is a very, very, very small changes in temperature across the sky. It is the closest thing to a perfect black body in the universe. So a black body is what physicists essentially call the radiation from something that's hot, so thermal radiation. So our sun emits thermal radiation. It's the amount of radiation it emits as a function of wavelength is given by the black body equation. A black body looks like something like this. It peaks at some temperature, and this is frequency across the bottom here, and intensity at like this. This here, the green line is the theoretical black body spectrum calculated by Planck in the late 1800s. The red is the data from the COBE satellite in the 1990s with a spectrum of the cosmic microwave background. You can see it does not deviate from the model, certainly within your eyes, right? So it's the closest black body in the universe. So pure thermal radiation. So, going to get a little more technical now, just to tell you where does the cosmic microwave background come from, right? So I said the universe was hotter in the past, and it's cooled down to a temperature of, say, 5 degrees nowadays. What are we actually seeing when we look at the cosmic microwave background? Well, very, very early in the universe, radiation, so light and matter, things that we're used to, like electrons, protons, neutrons, what we call coupled. The two things were sort of weren't able to vary freely from each other. As the universe expands, the temperature drops, and below a temperature of about 10 to 10 degrees Kelvin, you start to get effects that start to let radiation act differently from matter, what we call decoupling. And when you get below about 1 billion degrees Kelvin, you get cool enough that you can start to form deuterium. Deuterium is a type of hydrogen. And electrons combine with the nuclei to give you neutral atoms. And so for the very first time, you have neutral atoms in the universe. Before that, it was too hot. You just had protons, neutrons, and electrons. This is what we call recombination. And when recombination happens, when you start to form the first atoms in the universe, you then allow the radiation to travel freely. And the universe is then transparent to photons, to radiation. And this is what we call the surface of Ladd scattering. Right? So when we start to form the atoms, the matter and radiation decouple, and the photons stop scattering off the electrons in the universe. This is similar to thinking about a cloudy sky, right? What we see when we look at clouds is the bottom of the cloud, right? That's the last time the photons scatter off the water vapor in the clouds, okay? So that's the surface of Ladd scattering when we look at clouds at the bottom of the cloud, okay? In the early universe, the surface of Ladd scattering is just before, just round about, we start to form these neutral atoms, right? And so then the photons can travel freely and they can actually reach us. This occurred in a redshift of 1,100. I'm sure many of you probably keep track of or maybe some of you keep track of the highest redshift object detected, right? Well, as you know, we've never come even close to getting anywhere to 1,100, right? Temperature of the universe at the time was about 3,000 degrees Kelvin, and it was about 1,000 times smaller than the universe currently is today. So the surface of Ladd scattering actually has some thickness. If you think about, say, the surface of the sun, the surface of the sun that we see is actually the photosphere, and the photosphere has some thickness, right? It's not just some restricted surface that has a thickness. In the same way, the surface of Ladd scattering has some thickness, and the thickness is essentially as the universe is cooling down and forming more atoms. This is essentially, well, it is the furthest back in the universe we can see with photons. Before that, the photons were always scattering. So the surface of Ladd scattering, the cosmic microwave background, is the earliest you can actually see in terms of radiation backwards in the universe. Okay, but the discovery of the cosmic microwave background, this cold radiation that's permeating all the way through the universe, anywhere we look, leads to two big problems. Problem problems with the Big Bang Theory that need explaining. The first is, why is the cosmic microwave background so smooth, right? Why is its temperature essentially the same to 1 part in 10 to the 5 Kelvin? It's just called the horizon problem, and I'll describe that on the next slide. Another question is, why is the geometry of the universe so close to being flat? So, it's just known as the flatness problem, and I'll go into a little more detail about what both of these problems are. So, cosmic microwave background is smooth in all directions. So why? This is what we call time versus space. This is what we call light cones. Essentially, anything within this light cone is what we call causally connected. It means that light can have traveled between two of the spaces in the age of the time of the universe since then. Right? So parts B and C are far enough apart that light could have traveled from B to C by the time that we see it at A. Right? That makes sense. Any parts outside of here are so far apart that light cannot travel from one side of the universe to the other side of the universe, and the universe knows about the other part at that given time. Okay? What we call causally connected. And it turns out that any part in the sky that's more than 2 degrees apart would not have been in causal connection at the time of the last scattering. So what this means is that when this last scattering happened, one side of the universe didn't know about the other side of the universe, right? Yet they have the same temperature. So how's that, right? If one side of the universe can't have known about the other side of the universe because there's not been enough time for light to travel from one side to the other, why are they the same temperature? This is the horizon problem. Flatness problem. So we're very familiar with space being flat, right, here on Earth. If we think about everything we think about, if we draw a triangle on a piece of paper, we know that the angles are up to 180 degrees, right? But turns out space doesn't have to be flat, right? It can be curved. It could be curved like a sphere, closed universe. It could be open like a saddle, a horse's saddle. Or it can be flat. I mean, it could be any of these. But why is it flat, right? If you think about, sort of just give you an idea of the sort of different geometries you can have. If you think about the Earth, right? If you start out at the North Pole and you travel down the meridian to the equator, okay? And then you turn east by 90 degrees, and you travel a quarter of a way around the globe, okay? And then you turn north by 90 degrees, and you get all the way to the top, okay? And then you find that when you join those lines up and you get to the top, the angle between the path you started on, the path you joined up is 90 degrees. So you've got a triangle, you turn 90 degrees twice, right? You have a triangle, you have 3 lines joined together, right? But the angles add up to more than 180 degrees, right? So in curved space, i.e. the surface of the Earth, angles behave differently, right? So triangle that you're familiar with, we know adds up to 180, should add up to 180 degrees, doesn't it, right? So space can be different shapes. If you have a curved open space like this, the angles will add up to less than 180 degrees. But why is it a problem that the universe is flat? Well, the reason is that flat is such an unstable equilibrium point. Right? You're familiar with unstable equilibrium points. If you think about a pencil, right? If you were to balance a pencil on its point, right? If you were to get it just so it would stay like that, right? But if it was the tiniest movement, that pencil would fall right over. It would never go back to standing up without you intervening, right? Or if you have a ball sitting on the top of a hill, and the ball will sit there quite nicely until you push it in one direction, right? And the ball rolls all the way down to the bottom, right? And it never goes back up to the top, right? So it's an unstable equilibrium point. Well, the universe being flat is an unstable equilibrium point. A tiny little bit more matter in the universe, and the universe would collapse. Right? It would be closed. A tiny bit less matter in the universe, and the universe would just keep on expanding forever. Right? Yet, what we have is a universe that's almost perfectly flat. Current best cosmology shows that we're very, very close to having a flat universe. And if you extrapolate backwards in time, it tells you that it had to be 10 to the negative 62 away from being perfectly flat in the very, very early universe. Right? So it has to be one about as exactly as you can ever get. Right? And so the question is, why is the universe so flat? Right? And this is such an unstable equilibrium point. Why is it like that? The solution to both these problems was first suggested by Alan Guth in 1980. And he said, well, if you go far enough back into the very, very, very early universes, just as after it was born, then the universe everywhere should be in causal connection, right? The universe is not old enough that things are far enough apart yet, and everything can still talk to everywhere else, right? There's enough time that light can travel from one side of the universe to the other. Okay. And the universe is in stable equilibrium at the time. And then he says, well, if you then have, for some reason, a tremendous spurt of expansion, the universe grows exponentially rapidly, you can solve both your flatness and your horizon problems. And when I say exponential expansion, he talks about we talk about something like 40 orders of magnitude in size, right? So 10 times 10, 40 times, in a time scale of 10 to the minus 34 seconds. Right? So this is 40 magnitudes of increase in the size of the universe in 10 to the minus 34 seconds. And this smooths out the universe. Essentially, any little wiggles were there, it gets stretched out. If you think about, say, holding a plastic bag, if you stretch your plastic bag, all the creases that are in there all flatten out, right? And it also acts to make the universe flat. Again, the stretching ends up doing that. And so if you have inflation, you can solve both your horizon problem and your flatness problem. And then you say you have this, after 10 to the minus 34 seconds, you stop expanding like this, and the universe then begins happening in exactly the way we expect from the sort of standard Big Bang theory. Okay, so this sounds like pie in the sky stuff, right? This is kind of ridiculous when you say 40 orders of magnitude in 10 to the minus 34 seconds. But there's actually physics behind this that tries to explain how you can actually have this happen. And it boils down to essentially what people like to call a theory of everything, right? The sort of one of the ultimate goals of fundamental physics is trying to come up with a theory that unifies gravity, electromagnetism, and the strong and the weak forces. And it's thought that in the very, very early universe, that's exactly what happened. All those forces were unified together in one theory, or they all work together. This is called the grand unified theory. And inflation begins at the very end of this grand unified theory era, just before gravity becomes a separate force. So here we have four forces: gravity, the weak nuclear force, the electromagnetic force, and the strong nuclear force. These are the four fundamental forces of nature. If they're all unified at the beginning, inflation happens just when gravity splits off. You have what we call, technically called spontaneous symmetry breaking. Because these theories have lots of symmetries in them. You may have heard of string theory, and they like to have all these symmetries in them. The spontaneous symmetry breaking is what happens when these sort of these different forces all break off. And so, what happens is, in the early universe then, somehow the universe gets into what we call a false vacuum. So a vacuum, or is what we call is essentially the lowest energy state the universe can be in. Everything wants to be in the lowest energy state it can be in. Right? But if the universe cools a little too quickly, it can get into what is called the false vacuum. Not quite the lowest energy state, but a low enough energy state that it can't suddenly jump from that state to another. And a sort of comparison that you may have heard of is supercooled water. Have you ever come across supercooled water? I have this YouTube video that I hope works. But,
liquid below 0 C.
yeah, so this is when you get water that is liquid below 0 C. That's right. Let me try and get this.
I think 105 degrees angle molecule is well. That's very simple.
That will be 1 second. This is actually done by a high school, which is kind of a really nice demonstration. They get a bottle of pure water, they freeze it super quickly down to 10 below freezing. This is it's just come out. They bash it, make one knock, and it freezes instantly. Right? All they've done here is cool this thing very, very quickly. It gets into this false vacuum state where it's it wants to be, it's this lowest energy state is being frozen, yet it's not frozen, it's still liquid, right? But as soon as you bash it, instantly the whole thing changes to ice. Here's another example. They open the bottle and they pour it on a cool piece of glass. And you see, as soon as it touches it, it starts to freeze. Right? So this is kind of the closest analogy we have to what a false vacuum is, right? So you can think of the universe as being in a state that's like the liquid in the bottle, right? So it's still liquid, but it really wants to be frozen, right? So the universe is in this state, false vacuum, but it actually really wants to be in a different state, right? It wants to be frozen just like in a different state, just like the water wants to be in a different state. Okay, and so what happens is, just in the same way that if you bash that bottle of supercooled water, right, it instantly goes into this other state. Well, what happens in the idea of behind inflation is that you actually have, instead of bashing the universe, you have what are called quantum fluctuations, right? So the universe is so, everything, there's a thing called Heisenberg's uncertainty principle that tells you that you can't know the position and momentum of something exactly. And so things can fluctuate, and particles can come in and out of existence. And what you can have is one of these fluctuations makes the jump to the lowest energy state, right? So in the same way that as soon as one ice crystal starts to form, everything else becomes ice in the supercooled water. In the early universe, as soon as one part of the universe makes a jump to the lowest energy state, the rest of it does too. Okay? And it's that jump, in the same way that water cools very, very quickly and forms ice very, very quickly. What's happening here is that the universe expands extremely quickly, right? So, and it blows up to being very, very big, very, very quickly. And then inflation stops when you start to, you get cold enough that the gravity could break off from the rest of the force, it becomes a force. And in the same way that when water freezes, it releases latent heat. As the universe ends its inflation, it gets heated back up to be very, very hot. So this is showing you the sort of size of the universe, the temperature of the universe is a function of time. It cools down, and then during inflation, it gets very, very cold very quickly. And when inflation ends, it jumps up again and becomes the temperature it would have been before. And here is the size of the universe, this line here. So it's small, and then it jumps up very, very quickly during inflation and keeps on expanding. Right? So the idea is you have this exponential expansion very, very quickly early in the universe. Okay, so the story gets, we want to talk about why we see evidence for gravitational waves, why we should have gravitational waves early in the universe. Well, inflation can't perfectly smooth out the universe. Quantum mechanics tells us that there always has to be some fluctuations, things can't be exact. And there are two types of things that can fluctuate in the early universe. There's the gravitational field, and there's what we call the inflaton field, which you don't have to worry what this thing means. These fluctuations of the inflaton field lead to changes in the density of the universe at early times. Changes in the gravitational field lead to gravitational waves. So, if you want to be able to prove this has happened, right, that there's this thing called inflation that does this ridiculous expansion in a very, very short time, you have to be able to show that there are density perturbations, and you'd like to be able to see some evidence for gravitational waves from early in the universe. Turns out density perturbations are not that hard to see, and I'll show you the evidence for that. And what BICEP2 has been doing is been trying to detect these gravitational waves from the early part of the universe. And both of these should be imprinted on the cosmic microwave background. Okay, these are the temperature fluctuations in the cosmic microwave background. Red are the slightly hotter regions, blue are the colder regions, and again, this is drawn to highlight the changes. These are so very, very minuscule changes in temperature, right? It's the same temperature within 1 part in 10 to the 5. These changes in temperature, these are set by density changes in the early universe. Essentially what happens is that as you start to form matter, you get some denser regions and some less dense regions, and the photons, the light, trying to get out of those denser regions have to do more work against gravity. So they actually get what we call a gravitational redshift. And so that makes them slightly colder. Okay? Those in less dense regions have to do less work and so slightly hotter, so you get these temperature changes that mimic the density changes that we see in the early universe. Another way of plotting this is basically showing the size of the temperature fluctuations as a distance of angular scale. So if we think about how far are 2 points on this diagram, the further apart they are, the bigger the number along here. So this thing peaks, and you see these oscillations. And these are what we call baryonic acoustic oscillations. These things, essentially sound waves in the early universe, right? And these are set by the fact that there are these density perturbations in the early universe. So you can think of it something like this: that in the early universe, you end up forming a whole bunch of sound waves, and those things are imprinted today on the sort of density of where the galaxies are in the sky. And exactly what those temperature changes look like in the sky is set by what the geometry of the universe is. So if you think about if the universe is open, flat, or closed, temperature changes would either look very close to each other, or very far apart from each other, or just about what we see, right? It turns out a whole bunch of other properties of the universe can change this. So how the universe is curved, how much baryons, so how much matter-like protons, electrons, hydrogen, helium are in the universe, how much total matter that includes dark matter, or how much dark energy there is. Exactly the oscillations that we see are set by all these things, and you can actually measure them and figure out the properties of the early universe. But this is only telling us about the density perturbations. So those are the quantum fluctuations of the inflaton field. Right? This doesn't tell us about these gravitational fluctuations, the gravitational waves that we'd really hope to be able to see. And that, detecting the gravitational waves, would be the smoking gun of inflation having happened. The question is, how do you go about detecting gravitational waves in an extremely early universe? It turns out you can do it with polarization. So you probably, many of you are probably familiar with polarization. Light can be emitting in all directions. If you put a polarizer in the way, then it makes it go in only one direction. So you probably all have owned a pair of polarized sunglasses or have a polarized lens for your camera, right? It's just doing this. When light scatters off puddles of water, or it becomes polarized, right, in a particular direction. So your polarized lenses actually filter that out and let you just see one direction. It actually gets rid of the glare that you technically see when you're looking at sunshine shining off a pool of water. So light can be polarized, right? And it turns out that the gravitational waves actually can make light be polarized in a particular way. And you can make light be polarized in a particular way if you have fluctuations in a particular direction. So if there's some preferred direction in the universe, right? So if you think about a wave of water, right, as if you have two things floating on water, right, as the wave passes by, those things get either pushed together or moved apart, right? These things change, and the direction of the water wave traveling is a preferred direction, right? So those preferred direction can actually imprint a polarization signal on the light, right? So if you have these gravity waves traveling through the early universe, they can imprint on the light and give you a polarized signal. Now, there are different types of polarized signals. You can have what we call an E-mode polarization, and you can get this from a whole bunch of different things. And in the early universe, you see this from those acoustic oscillations we've already talked about. And then what BICEP2 was looking at was what we call these B-mode oscillations. And this is what you get, B-mode polarization. And this is what you'd see if you expect, if you have gravitational waves in the early universe. Just remember this pattern, a curved pattern like this of vectors. This is indicating which way the light is sort of polarized. Remember this picture, because I'll show you this in the real data. So what was BICEP2 doing? It's a telescope on the South Pole that operates at 150 gigahertz. It was designed specifically to go after polarization of the cosmic microwave background, right? The people have predicted that you should see gravity waves from the polarized cosmic microwave background, right? And so this experiment is done specifically to do this. In terms of big astronomy experiments, this is extremely cheap. $10 million is a very small research project for a telescope, right? If you think about the James Webb Space Telescope that's going to be launched, its budget is something more like $10 billion, right? So $10 million is very, very small in terms of this sort of thing. It's led by 4 institutes, Harvard, Stanford, Caltech, and Minnesota. Said its sole goal is to do these polarizations effectively. And this is what they found. At the top here is the E-mode signals. You can ignore this. On the bottom here is the B-mode signal. If you remember, I talked about those curled vectors. If you can see these tiny little lines here, you can see how they're curled around, right? And the colors have been chosen to show you where the centers of this sort of curling is happening, right? So around this red bit here, you can see the curling happening in a particular direction. So, what they do is they compare their observations with some simulations, and you can see here that this red bit is much, much stronger than what they see from simulations if you didn't have gravity waves. So they try and convince you that they've seen gravity waves by showing that their signal is much stronger than what you expect from simulations. Now here comes the bit that has become controversial. The question is this signal due to gravity waves, or is it due to something else? Okay. So is there anything else that can give you this B-mode polarization of light? But it turns out dust in our galaxy can give you that signal, okay? As well as a process called galactic synchrotron emission. In their original paper, they try very carefully to model this. They actually look at what the dust is in that particular part of the sky, and they try and correct for that, and they rule dust out at a relatively low significance, only 2 sigma. They rule dust out, being the origin for this signal. This has now become a really contentious thing, okay, and I'll talk about why this has become contentious recently. So they made a big hoo-ha, they had a big press release, they had at Harvard, they went to Andre Linde's house, who was one of the people who started inflation back in the early 80s, and bought him a bottle of champagne and told him that everything was solved. And they claim that they detect the gravity waves at some high significance. So is this the first direct detection of gravity waves? Well, it depends on your view of what a direct detection is, right? You can take an analogy of taking a picture of waves in a pond. It's essentially what they're doing, right? And it's very different from other ways of detecting gravity waves. I would say, yes, it's a direct detection if this signal is real, right? Another famous indirect detection of gravity waves was the Hulse-Taylor binary pulsar system, which is where these 2 pulsars were seen to their orbit was seen to change over time in exactly the way you'd expect from gravity waves. But, as I said, this is controversial. The BICEP team sort of jumped the gun, right? They had their answers, they wrote their paper, and they were so confident that they wanted to release the results and make an announcement before the results had been through what we call the peer review process. So, many of you may be familiar that when you write a scientific paper and you submit it to a journal to be published, it gets refereed by typically 2 or 1, 2 or more referees. So the editor typically chooses someone who's an expert in that area and says, please critique this paper. Is this paper correct? Do they do anything obviously wrong, right? And so for you to believe anything, typically you wait till something's been accepted for publication, has been through this peer review process. So BICEP2 made their announcement before they'd submitted their paper to the journal. They made it the same day they submitted it, right? Because they didn't want to lose the game, right? They wanted to be the first. That was their first mistake that got them quite a bit of criticism, I would say. The second mistake was that they didn't have the full dust maps. It turns out that they did. They'd been at a conference and they'd seen results from the Planck telescope. Planck was a satellite that the European Space Agency put up that was also looking at cosmic microwave background. It was looking at the whole sky and was getting very nice maps of the dust. And they were at their conference, they saw the slide of the dust maps. They took the picture of the slide and they used that as their input for their model for what the dust should be. So they didn't actually have the real data, they just took a picture from the conference presentation. Oops. Yeah, so that's pretty bad, right? And And it turns out that now, Planck have just released their dust maps. It's been published in a peer-reviewed paper, right, that came out just like 2 weeks ago. And I should say the initial indications don't look good for the BICEP2 result. In that it appears that dust may actually be the origin of this B-mode polarization. They do have a get-out clause. At the very end of the Planck paper, the abstract of the paper, they say, Planck and the BICEP2 teams are working on a joint analysis of the data to get the best sensitivity and see if there is a real BICEP2 signal, a real B-mode polarization signal. But I'll show you this, and I think this basically, most people don't believe the result after having seen this. This is showing the strength of the B-mode polarization on this axis, and this is a function of angle in the sky. Black line is the best fitting model from BICEP2 with their gravitational wave detection. Blue, shaded, is the data for what you would expect to get from dust based on the Planck dust map data.
Wow.
And you can see these two overlap pretty well, right? And so I think most people have seen this. I think most people no longer believe this BICEP2 result. But I still think there's some hope, right? This signal should be there if inflation is right. So they're working very, very hard to do this. And there's still hope that we may be able to pull something out of the data, right? When the two teams work together, they should hopefully be able to get much better sensitivity. And look for this. There are multiple different techniques they could use, actually. This is kind of a crude way of showing it. There are multiple different techniques they can use to try and get the signal out. And there's still a small hope that they may do it. And I would say if they do it, it is definitely a Nobel Prize, right? But when the Nobel Prize in Physics comes out tomorrow, I do not expect it to be from BICEP2. On that bombshell, I'll stop there. Thank you.
We do have time for just a small number of questions. Yes.
Is it possible that the B-mode polarization is just merely correlated with dust and not actually having causation?
That's a good question. That could be, it would be a horrible coincidence if that was true. Right? So, if you look at I don't have the figure here, but if you actually look at the dust maps, BICEP2 only look at a very small region of the sky, and Planck look at the whole sky, and when you look at the whole sky, you can see how the dust changes over the part of the sky, over the sky. BICEP2 had chosen that region because they thought there was less dust there. It turns out, based on the Planck maps, it's not quite as little dust there as they thought. But given the changes in dust across the whole sky, it would be a very horrible coincidence if the signals were just so that they match right up. I would say it's possible, but I think it would be, it would be unlucky.
Is it possible to look at
Louder, please.
Is it possible to look at two different directions in the sky, one in the direction of a lot of dust and another direction where there isn't as much, and subtract out the...
Yeah, so you would hope to try and look somewhere else in the sky and do this too. And presumably they're going to try and do something similar. Other things to do is look at multiple different frequencies. So BICEP2, they released their results only using data from 150 gigahertz. If you have multiple different frequencies, you can actually separate the difference between dust, the effects of dust and the effects of gravity.
All in a single direction.
And even in a single direction, right? And so there is hope that they can do that, actually. So the Planck, for instance, looks at multiple different frequencies, so they should be able to hopefully do that.
So maybe just a matter of time.
It may just be a matter of time, yeah.
My question is, about how much time do you calculate that the process of resolution will take?
So, sorry, could you repeat your question again to me?
How long do you think it will take before they can resolve
Resolve the issue.
correlation or discorrelation?
So the question was how long will it take to resolve the issues, whether there's a correlation or not. I would say that Planck and BICEP2 are working together right now. I would suspect it would be within the next year. Planck finished taking data a couple of years ago, so they've been working very, very hard on their analysis for the last couple of years. They're not taking more data, so you shouldn't be waiting for more data to come in. It should be happening relatively soon.
What is dust? Can you define dust? And is it uniform?
So in astronomy, dust essentially means anything that's made of silicates, right? So and that are very, very small particles. Is it uniform? No. It could be made of a bunch of different things, right? I mean, the galaxy is full of it, right? Essentially just complex molecules of silicate molecules.
So it's not uniform.
It's not necessarily uniform, no.
I was just wondering, are you a member of the group that buys inflation, or do we need to go back and start from the beginning?
I would say virtually everybody buys inflation. Freshman astronomers taught in every class on the universe. It's brought into by basically everyone, right? Because it nicely solves these issues, right?
And add-on, you didn't talk about it, but astrophysicists like Max Tegmark, a fellow by the name of Green,
Yeah.
would have you believe that inflation leads inevitably to a multiverse.
So
Is that viable also?
yeah, you're almost getting into philosophy when you start talking about it. Because there's no way that scientifically you'll be able to show whether you have one or not. So from that standpoint, I'd say it's pure speculation. I mean, it comes out of some of their theories, right? That if you have some way of forming our universe, presumably there's some way of forming other universes. Which actually is what it boils down to. But that's philosophy, not physics.
Well, let's thank our speakers.